firstly, I'm going to send a list around. It has your traveling arrangements. So it's literally your name and then the two groups that will be departing on Friday from the res, and just mark if your name is there and whether it is correct with which group you are, or if you're at the bottom of the list where you need no arrangements, just tick there that you're good as well. Okay.
What if you have a special arrangement, like you leave a day early?
Check if your name is on the list or not, but I'll make sure with Dirk whether all of that is in order as well. Okay, great. So I wrote 2 challenge questions up there. That is for you that already know the work we're going to start with right now. If you don't know this work, please don't attempt the challenge questions. And there are other focus on what we're doing here. So, and if you want the answer afterwards, you can come check with me whether what you got is correct or just find out how to solve it. Okay. So today we're going to start with counting methods. And this is going to be just basically how to count stuff, and then we're going to move on to what we call permutations and combinations. Okay, so very quick example there. If you have to make a 3-letter word and you only have the letters A, B, C, and they may be repeated, in how many ways can we do that? That's what we want to find. 27. Okay, so I'm just going to go quickly through this. It's a 3-letter word, so you basically have 3 gaps where you need to place letters, right? Because it's a 3-letter word, and you have 3 letters to choose from, A, B, or C. So in the first position, there can be a B, or a C. So you have 3 options. In the second position, because repetitions are allowed, you again have 3 options, A, or B, or C. So you also have 3. And in the last position, again, you have 3 options, A, or B, or C. And this gives you 27 possible 3-letter words that you can make from the words A, B, C when you are allowed to repeat them. So we're going to do a lot of variations that goes about whether you're allowed to repeat letters or not, and whether the orders of the letters are relevant or not. So obviously when you make words, the order is quite important. And I'm just saying with these type of problems, we call them words, but you might recognize A, B, C is not a word itself, but we're counting it as a word. So it doesn't need to be a senseful word, just a word. Okay, great. So this leads us to a theorem. If we basically just generalize our result there, which says that there are n to the power of k different sequences of length k that can be formed from elements of a set X consisting of 4 elements. N in that case is we have 3 elements, and we also have a 3-letter word. So both n and k in that example is 3, and that's how we got to our 27. Now our next example is very similar, but in this case they're not allowed to repeat. So I'm just going to do this one quickly as well. So again, n is 3. We have 3 options to choose from. It is still a 3-letter word that we're dealing with, so there's 3 positions to put letters in. For the first position, we have 3 options. We have our set of A, B, C, and we have not removed any of them. Okay, you're good. Okay, so for the first one, we have 3 options, either A or B or C. So for instance, if our letter would start with A, if we chose A, we took an element from our set of 3 elements, and it is no longer in that set. So for the second position, we no longer have 3 options. We now only have 2 options to choose from, because they may not be repeated. So there's 2, right? Because for instance, we took A, so we only have B and C left to choose. So let's say we choose C, there we put C in. And then for our last position, we already took 2 out of the 3 elements out of the set, so we only have 1 element left. Right, and this must be B because there's nothing left in the set. Right. So this is what we call permutations. Just gonna write this down. So for this was permutation with repetition. And for our second example, this is now permutation without repetition. Right. What does the word permutation mean? So I did actually Google the definition because it's so weird describing this. And it basically says it's several possible ways in which a set or number of things can be ordered or arranged. Do I need to write that down? Good. So it's basically just this number of ways that a set of things, and the important thing here is it can be ordered. And we're counting every different ordering as a different permutation of that set. Okay, any other questions about this? Okay, so this one also has a bit more of a general theorem. Is our generalization of our previous example, which says if you have n objects, and distinguishable just means they're different. They're not all identical and the same object, and the number of possibilities to organize, to arrange them or order them in a row is n times n minus 1, and so forth. And you'll see this is different from the previous one because their n stayed the same. It was n times n times m. In this case, because we can't repeat them, it decreases by 1 every time. Right, so just mathematically, an easier way to write this is the factorial function. Okay, so we say n and then an exclamation mark. It's not just a very excited n. We call the factorial function, which is n, and then we say n factorial is equal to this. So if we just take a few other examples, if I have 6 factorial, 6 is equal to 6 times 5 times 4 times 3 times 2 times 1. Right? 2 factorial, 2 times 1. 100 factorial, 100 times 99 times, so you go on until you reach 1. Right? 1 factorial would be 1. What would 0 factorial be? 1. Right. Why?
Because there's one way to arrange 0 objects.
Right. So our theorem says the number of possibilities to arrange n objects in a row is n factorial. So if we want to arrange 0 objects in a row, well, there's one way to do it because you have 0 objects. It's a bit of a strange mindset. You can also prove it algebraically, which I'm just quickly going to do for those of you who's not completely convinced that we can arrange 0 objects in one way. So for any if we do k factorial, it's k times k minus 1, and so forth, right? So you can basically go write k factorial as being k times k minus 1 factorial, correct? Great. So that would mean that you can write k minus 1 factorial as being equal to k factorial over k. Okay? So in this sense, if we let k be equal to 1, then on the left-hand side we would get 1 minus 1, that's 0 factorial. And on the right-hand side we'd get 1 factorial over 1, which is, well, as we said, 1 over 1, which is 1. Okay. Let's move on to our next example. That one and write the next example as well. Great, so the two examples are only slightly different. Example 3, what's the answer there?
10.
Okay, 10 factorial, someone just said it. So it is 10 factorial, and that's because you have 10 positions, 1 to 10, you can write them all out, and in each position a student needs to be, and we can clearly see that order is important here. Whether you're first or 10th, it's quite important. And also, students can't be repeated. You can't be second and third at the same time. Then, for example, 4, we again have 10 students, but in this case, we don't care about everyone that's fourth and onwards. We only care about first, second, and third. So,
10 choose 3.
10 choose 3. And what is 10 choose 3? 10 factorial. Oh, you guys are smart. Have you figured out the challenge question yet? Anyone?
John? Close.
Close. Oh, great. We've got someone attempting. Okay, great. So the thing here is you have 3 positions again, because we only care about first, second, third. In the first position, there's 10 students that could be first, so you have 10 options. in the second position for students already out of the game, so you only have 9 and then 8. Alternatively, we could go write this as 10 factorial over 7 factorial. Alright? And we refer to this as being 10. So this is permutation, sorry.
It's not choose.
You need 10 factorial over 3 factorial, 7 times 7 factorial.
Yeah, it's not choose. It's just permutations.
Yeah.
That's
You're happy with this? 10 factorial over 7 factorial? Right? Is there any issues with this? 10 factorial over 7 factorial? Okay, it's not choose. So we'll come to choose and permutations right now, but this is going to be what we call a permutation, which is not like that, but it's a notation to write it is 10 choose 3 in this case, not 7. Right. 10 minus 3. So we're going to write this first.
That was correct.
Yes, I just want to write this a bit better. 10 minus 3 factorial. And this 10. Right. Okay. Sorry about that. Okay. That's why wording here is quite important, because we often talk about combinations as if order is important, but we'll see now that the difference between permutations, which is what we just did, and combinations does not depend on order. So when you say my LOX combination is 1, 2, 3, it's actually your LOX permutation, not combination. Okay, so a theorem about what we did there. Just another generalization. We write it as N and then a P and K. Okay. Now that's it. There we go. Okay, there's a few other notations, but they basically all have a P in them. Yeah.
In that second question, we can only move to the right and up arrow.
I'm sorry, for those attempting this challenge question, it is quite vague in a lot of ways. I'm just quickly going to draw a smaller scale version of it, just for those who are attempting it. Don't stress if you're not attempting it right now. So this, it's obviously just going to be 8 by 8 or 10 by 10. It is 8 by 8. Okay, so the diagonal we're going to talk about is the line going through there. Okay? So basically the bottom left, other way around. Sorry about that. We care about this diagonal. Okay. So from the bottom left, you want to go to the top right. And we're saying we want to find out the amount of ways you can get there. So you either go upwards here, and then you can only move to the right and upwards through all the points there to get to this point, which means you can move here, but you can't go right again. You can only go up from there on, and then either up or right again, all the way to get there. Or alternatively, you can go for the bottom hemisphere. They should give the same number of ways. You can go right here, and then you can only go up and right. So you can again move to that one, and then this way is your only option. Okay, any questions about that problem? Okay, sorry, it was quite vague in the problem description. Okay, great. Another example. Sorry. That is. Sorry, guys. Only one math team of 4 students. Yes?
Answer for number 1 of each question. I was just say that is
What's your guess for it?
89.
It is 89, well done. Okay. Okay, great. So in this case, what makes this different from the previous examples? Anyone? Yes? Oh. I haven't worked it out, but it could be.
That sounds like more.
Yeah?
Taking A, B, students A, B, and C, and D is the same as taking students D, A, B, and C.
Exactly. So the difference now is we're choosing a team. Whether A, B, and C is in a team and C, B, and A is in a team, it's the same team, like he said. So in this case, the order is no longer important. So there's still, just going to write here, no repetition, obviously. Is there any questions? Okay, but also no order. Alright. So what we did previously was you would say, like we did in the previous example, you would say 10 factorial over 6 factorial because there was 4 spots. But the problem with this is we're thinking about this as if the 4 team members, the order in which they were chosen is relevant, which it is not in this case. So what do we have to do to this to make our problem accurate, our answer accurate?
Divide by 4 factorial.
Divide by 4 factorial. So what we basically did is we said we have 4 spots for the team, and we're treating it as if order is important. So we're going to say there's 10 people for the first spot, 9 for the second, 8 for the third, and 7 for the last one, which gives us this. But then we're saying we don't care in which order this is. So the amount of ways you could arrange these 4 team members is 4 factorial ways. Does that make sense? So we have 4 factorial, a multiple of 4 factorial, too many teams. So we have to divide by 4 factorial then. Okay. So we first pretended that order is still important by saying we're just going to choose 4 as in with their ordering number 1, number 2, number 3, number 4. And after we chose those 4 in positions, we're going to say, okay, but now we're going to just completely throw out the idea that they have a certain position in the team, because they are just a team as a whole. So we're going to divide by the value that we basically overcounted by. Any questions about this? Anyone still uncertain? Okay, so what we wrote here is what we describe as being our choose function, right? So we basically there had 10 factorial over 10 minus 4 factorial times 4 factorial, right? And we can rewrite this as 10 choose 4. Alternatively, you can also write it as a choose, and you have 10 choose 4. And that's where the permutation combination looks quite similar but means a different thing. Okay, so this is a typical setup to assume, to take it as if there is order and then divide by the overcounting for order.
Quick question for number 2 on the challenge.
Yes.
If you go like on the top, up, right, can you go left again?
If you're at the top, you can't go left, you can only go right.
So you can only go up and down.
Up and right, yes. Okay, great. Sure. We have another theorem for this. Okay. That theorem of what we call the choose function, and then just 2 nice properties about it is n choose k is 0 if k is greater than n or if k is smaller than 0. So we see this as being a set of n and you want to choose k elements from that. You cannot do that if k is greater than n. So if you have 5 kids and you need to pick a team of 6 from them, you can do that in no ways because you only have 5 to pick from. And then similarly, I can't choose -1 sweets from a pack of 50 sweets because it's not possible, so that's 0. And then the second property, n choose k, is also equal to n choose n minus k. And the mindset behind that is if you have a team of 5, or a group of 5, and you need to pick 3 students from that group of 5 students, you can do that. So if k is 3, n choose 3, but then there is 2 left. So it is the same as picking 2 students, and then there's 3 left. Does that mindset make sense? Anyone? Any questions so far? Okay, so that's 2 nice properties. Does anyone have the time at the moment? I don't want to.
It is 2:30.
2:30. Okay, great. What do you mean together?
So you can't separate the couple.
As in the 2 people in the couple?
Yes.
Well, they're a couple, so. No, if I'm understanding you correctly.
Is it 7 factorial?
Say again?
Is it 7 factorial? It's the answer.
Yes, is it?
7 factorial.
Oh, 7 factorial. No. Not even. Okay. In this question, the couples are different or distinct though. So you have couple 1, couple 2, couple 3, and couple 4. Alright. Okay, so if you switch couple 1 and couple 2, that is a different set of couples. Yes? 4 factorial. Also not.
8 choose 2.
Also not. So you only choose 2 of the. You want 4 different couples.
I think 7 plus 6 plus 5, 4, 3, 2.
Good shot, but not yet. Okay, so how we're going to see this problem is you have 8 people, right? So 8 people, 8 positions. 2, 3. Right. Okay, so we're seeing it as 8 positions, but we're going to divide these 8 positions into 4 couples, right? So this is going to be couple 1. This is going to be couple 2. Here we have couple 3, and then lastly couple 4. Okay, so if I tell you John and Mary is a couple, then Mary and John is also a couple, and it's one couple. So if these 2 people switch, it doesn't change. Yes?
Well, can you guess?
You want to take a guess?
8 factorial
Divide
divided by 2.
by 2. Almost, but not yet. So in this case, we have the number of ways to arrange these 8 people just standing in a row would be 8 factorial. We all agree on that. But the problem is So that gives us all possible combinations. But we overcounted here because we assumed that this and then switching is different couples, which it is not. And then similarly here, those two people switching we assumed as being different couples, which they are not. And so we go on. So for the first couple, we assumed them switching, but now we're going to divide to get rid of that. For the second couple, we did the same, as well as for the third couple, as well as for the fourth couple. So our answer is 8 factorial over 2 through 2 and 2 factorial. 4 2 factorials. Don't know how to say that in simpler sense. Okay, and this leads us to our next proof. Oh, not proof, theorem. There we have it. Yes?
Shouldn't we also divide by 4 factorial because the order in which we choose the couples
Those are
wouldn't
different.
matter?
Quickly want to check. Originally, I said in this case we are assuming couples 2, or couple 1 and 2, if we switch them as being a different set of couples. But in a sense, that doesn't really make sense for couples. For a better example, if you would say, I have 4 houses and I have 8 people to divide into couples to put in the houses, for instance, it would make sense that it matters whether it's couple 1, couple 2, couple 3, couple 4, and whether you switch them would be differently. But so if you would specify that, this would be the answer. But if you don't care about the couples, yes, dividing by 4 factorial would give you that couples and their order does not matter. As in couple 1, couple 2, if you switch them, it is still the same. Okay. Okay, another example. Anyone have an answer so far? Yeah?
I think it's 6 and 8 to the power 6.
No. Okay, so you would agree that we have 6 pieces of candy to choose from. Okay. So you'd all agree I could choose. Actually, I'm gonna start this side. Okay. 6 to choose from, and it would be valid if I chose. Let's say I chose chocolate, then a gummy, then another chocolate, and then there is 2 biscuits and another gummy. Right, that would be valid. I can't make up my mind, so I walk around and pick something else. Okay, I could also just go write this actually in order, which might just make the problem a bit easier. So just put the chocolates first, then the gummies, then the biscuits. I could also, if I wanted to, take 5 chocolates and then 1 gummy. I mean, there's a lot of different variations that I could pick. So, yes.
Is the order relevant? Are those 2 different options?
No, so they're the same option. I just rearranged to make it clear how many of each we took. Okay. So I could clearly divide here, put a line there, put a line here. 2 chocolates, 2 gummies, 2 biscuits, or 5 chocolates, and then just 1 gummy, and then no biscuits. Right? So then you'll see we basically have 2 numbers there as chocolates, a line, all the gummies, a line, all the biscuits. And then similarly here, all the chocolates, a line, all the gummies, a line, all the biscuits, which is none. Right? Okay. So how we can see this problem is
Is it 19?
I haven't actually worked it out. I only write it as a thing. So it could be, yes?
Is it 3 times 3 times 3 times 2?
No. Another hand here
3
somewhere?
to the 6.
3 to the 6. Also no.
So, 3 to the power 6 over 6 factorial.
Also not. So a nice way to see this is that you basically we have 6 lines and we have 2 bars, we're going to call them. So in total we have 8 positions here. Right? So wherever I put the bar is basically where I'm dividing between chocolates and gummies and between biscuits and gummies, right? So if I put the bar at the front and then so let's just ignore whatever we're writing there. That's 3, 4, 5, 6. If I put the bar there and a bar here, if we go with our same notation, it would mean we have 0 chocolates because everything before the first bar is chocolate. We have 3 gummies, we have a bar, and then we have 3 biscuits. Right? So this problem basically reduces to how many different positions there is to put this bars, 2 of them. Because these chocolates are all identical, we don't care whether we arranged the chocolates in different ways. So we have 6 positions plus 2 bars, that's 8 spots in total. And we basically only have to pick 2 positions to put that bars. And that's our answer. Someone could go work that out if you want to. I was a bit lazy. Okay, so our problem there basically reduces to writing it like this. And yeah. So we have a theorem that explains this a bit better. this 8 pick 2, 8 choose 2, sorry, we had 6 pieces of candy and 3 types of candy, right? Yeah?
You think I want
For this?
for that line with the line.
Okay, well, this is the answer. So we could basically write this as 6 plus 3 minus 1, choose 3 minus 1. Okay? So we had 6 spots and we had 3 to choose from. 3 different candies to choose. Plus 3 minus 1. Okay, let's see what the theorem says.
Is it pigeon nest?
Say again?
Is it pigeon nest?
Pigeon principle? No, not in this case. But it does resemble some things there. Okay. So. So this is basically what we did. Our set of check here. Yeah, we had 6 pieces of candy and no, 3 types of candy and 6 to pick from that, and it got us to this formula. Sorry, that is not the easiest way to have written this. To make it, sorry. So one of our properties that we showed up there is 8 choose 2 is also equal to 8 choose 6. And sorry, this is 6 plus 3 minus 1 choose 6. Sorry. That is easier, a lot easier to see. So our set of elements is the 3 types of candy that we have, right? Because that's what we're choosing things from. And we wanted to choose 6 of these 3 types of candy. And this is where the repetitions come in, because we can choose multiple chocolates or multiple gummies. Oh, sorry, I'm missing an R here. Number of ways to choose K elements, which in this case was 6. We had 6 spots, and of a set of N elements, which was 3. Okay. That is K. Here it is K minus 1. Like that. So this is our K, which was 6. And this is N plus K minus 1. If you just switch them around, then it resembles the formula exactly. Okay, and then that's it. Great. Okay. Just the last example for this. Which example is this? Probably like 7, 8. Okay. Okay, so this one's a bit different, or at least looks a bit different. Okay, anyone have an answer for it yet? Sorry, yes?
Question, does that non-negative mean that we can't use negative number?
Yes, so A, B, and C are all positive. It could be 0, but it's not negative.
102 and 3.
Choose?
102.
Yes? Is the final answer?
No, no.
Yeah.
102 and 3.
Okay, very close.
Very close.
Anyone know where we got the 102 from?
0, 0.
Hmm?
Because of zeros. I think that you can use 0.
You can
Or
do 0?
0. Right.
Yes. Anyone else close to an answer or have a guess? Okay, so.
Is this the challenge question or which was this now?
Oh no, we're
Oh, no.
example 8 at the top there. Yeah.
They have to be distinct. They can't be the same.
A, B, and C. They can be the same. They don't have to be distinct. That's a good question. Where's. Yes.
Does that put a matter?
Of A, B, and C. In this case, let's say yes, it does matter. We want to write it as a set A, B, C.
So you can have 100 plus 0 plus 0 and then 0 plus 0 plus 1.
Yes, that would be different sets in this case. Okay, so I'm going to continue on this side. Okay, so a nice way to go write it as the previous problem with the candies that we talked about is we go write the 100 out as the sum of 100 ones. Right? So you have 1 there, so it's just 1 plus 1 plus 1 plus, and so we go on until we reach 100. Right? So we have 100 positions here. That's all positions of ones. So basically, if we want to write it as A plus B plus C, we're basically just going to group ones together. For instance, if we wanted to group these ones together, we could say that's 3 and we make that equal to A. And then we go all the way till here and we say this is B and it's equal to 95. And then the last one is C is equal to 0. That could work. Alright? So what is this brackets we draw? That is basically equivalent to go drawing a bar there and a bar there. But for our bars method that we have, it says here the number of ways to choose k elements from a set of n elements, repetitions allowed. So we're choosing k from n. So what would our n be? How many positions do we have here in total? Oh, sorry, not how many positions. What would our n be? That's different questions. Well, there's actually two ways to see it. You could either go with the theorem, or you could talk it out. You could kind of explain it to yourself. So the way I prefer is saying how many positions is here, there, And it's the 100 positions for the ones, and then there will be 2 positions where we'll have to put bars. So in total, it's 100 ones plus 2 positions, so 102 positions, right? And we want to pick 2 positions to put that bars. Okay. Right, alternatively, you could use the theorem. Right, we have n elements to pick from, and our n is the 100 ones to pick from. And you want to divide it into 3 sets. You want to choose k elements. Sorry, that's a 3. Oh, I see. That is. Yeah, you still want to put it into 100 6 places. Yeah, sorry. You have the sorry. So if you want to use the formula, you have
It's 100 plus 3 minus 1.
yes, it's 100 plus 3 minus 1, but your k is 100. So you have 3 elements as in A, B, and C. So you basically have 3 elements, A, B, and C, and you want to take the 100 ones and divide them into each of these groups, either in A, or in B, or in C. So what you have here is 3 plus 100 minus 1, choose 100. So your k is 100 and your n is equal to 30. That's why the formula is a bit hard for me to visualize. I prefer talking about 102 positions and you choose 2 positions for the bars. Okay, I think that is my time. Okay, thank you guys. Are you done with the list? Yes.
What did you say? K minus 1 at the bottom.
K minus 1?
And then,
As in,
oh, no, no, no.
K is not 3,
Never
K
mind.
is
K
100.
is 100, not yours.
great. Is the list still in here?
How about we say instead of non-negative, we say positive instead? How will
It would make. It would mean that you can't have a bar here, and you also can't have 2 bars at the same spot. Just think we might. I'll work that one out for you. Okay, great. Everyone good? Okay. Just for those who did attempt the challenging questions, this one is 89, and the other one is 140. Okay. Good. You guys?
First one was just with an Archie.
Which one?
First one was with an Archie.
Yes.